Okay, so here is the answer key to test number 3. So problem number 1, the instructions say evaluate the logarithm. So we have log base 2 of the square root of 2. So what we know is the square root of 2 can be rewritten as 2 to the 1/2. And then there's a couple of ways to think of this. There is a rule in the book that says log base a of a to the n is always equal to n. Or you could use the third property of logarithms to bring that 1/2 out in front, and log base 2 of 2 is 1. Or just remembering that a logarithm means the exponent that would be put in this case on a base of 2 in order to result in 2 to the 1/2. Well, that exponent is 1/2. So 1/2 is your answer. Problem number 2, we are to write this in logarithmic form. So the base is 2, and then 1/4 is the argument, and the exponent is -2. So that means we have log base 2 of 1/4 equals -2. Now, a lot of people do like to put parentheses around the 1/4, but as long as it's clear that the 1/4 here is all in one piece here inside the logarithm, it doesn't really matter. Now let's go to the next problem, problem number 3. We have solve the equation. So that means we want to have what x is equal to in the simplest form possible. So if we rewrite this logarithmic equation in exponential form, we have 3 raised to a power of x is equal to 1 over 27. So 1 over 27, that is 1 over 3 cubed. And using what we know from elementary algebra about negative exponents, that means that's equal to 3 to the -3. So 3 to the x is equal to 3 to the -3. So the bases are the same, so that means the exponents must be equal, so x equals -3 is the correct answer to that. Now here we have problem number 4. Write the expression as a single logarithm with coefficient 1. So write as a logarithm. That means you're going to have a logarithm in your answer, and you're going to use those properties of logarithms. And coefficient 1 means there will be a 1 in front of the logarithm. So we don't have to write the 1, but we know that a coefficient of 1 is implied even if there is no number written in front of any kind of variable expression. So the 2 here becomes an exponent on the x because it's subtracted. There's a property of logarithms that says that the y needs to go down to the denominator. So log base a of x squared over y. And that's just using 2 of the properties of logarithms to do that. Problem number 5, you just need to punch the buttons correctly on your calculator. Most calculators that are not older than maybe 10 years old, you would just press the log, L-O-G button, log base 10 button, and then the calculator most likely is going to start parentheses for you. Put in your number, 2,966, close the parentheses, and then press equals. Some calculators, if they are an older calculator, you would put in the 2,966 first and then press the log button. On that type of calculator, you don't usually need to press the equals sign. Now on problem number 6, we're finding that hydronium ion concentration, like we did in several of the homework problems. So we use this formula. So first thing, multiply both sides by the -1. So we have -3.4 is equal to log base 10 of the thing we're looking for, the hydronium ion concentration. That's what that symbol stands for inside the brackets. So that's what we're trying to solve for here. So rewrite this problem in exponential form and you get 10 raised to a negative 3.4. So if we calculate that, just punch the buttons on our calculator, you should get 0.000398. Now, if you did the homework, all of these problems, the answers were written in scientific notation. So if we write this in scientific notation, rounded to the nearest tenth, that would be 4.0 times 10 to the negative 4. And that's because we move the decimal place 4 spots over so that we get it in scientific notation. Okay, here is problem number 7, and we're figuring out the decibels. The loudness of a sound is measured in decibels, and the formula is D, and that stands for decibels, is equal to 10 times the log of I divided by I sub 0, where I sub 0 is some starting level that we compare with, starting sound intensity level. So if you put 100 I sub 0 in place of the I up here, then the I sub 0 divides out and we just have 100. So I sub 0 is completely gone from this problem as soon as you plug in. Since log of 100 is equal to 2, we have 10 times 2, and that's 20. The next problem is just another punch it into your calculator, and very simple. So you just press the natural log button, the LN button on your calculator, and you should get for this negative 7.5890 rounded correctly to 4 decimal places. 4 decimal places always means 4 numbers past or to the right of the decimal point. Okay, problem number 9 is a little bit harder. In order to solve for x here, we notice that x is part of an exponent. So what we need to do is take the log of both sides. You can use either a common log or a natural log here. Does not matter, either one will work. So natural log of both sides is what I chose to do. And then the third property of logarithms says that we can bring the exponent down in front. So the 3x minus 1 comes down in front, and then we would, in order to start isolating the x, we could divide both sides by natural log 5. So natural log 5 is here. And then I did 2 steps at once on my answer key, and I probably shouldn't since I was going to scan this and show it to you. But the 2 steps are add 1 to both sides, and after you do that, divide by 3 or multiply by 1/3. So punching this on the calculator, it is extremely important that you completely calculate, you tell the calculator to completely figure out the inside of the brackets before you divide by this 3, represented by the 1/3 out here. If you don't tell the calculator to do that, you're most likely going to get the wrong answer out of your calculator. So 0.920 is the correct answer to the nearest thousandth. 1,000 has 3 zeros in it. That's a good way to remember that the nearest thousandth has 3 decimal places, or 3 numbers to the right of the decimal point. Okay, here is problem number 10, and we use our property of logarithms that says when we have the log of A plus the log of B, we can put that together into the product of A times B. So the log of A times B. So x times x plus 9 is x squared plus 9x. So we have log x squared plus 9x equals 1. So since log means log base 10, remember how we rewrite this into exponential form. That's the best way to go. So x squared plus 9x equals 10 to the first power, which is just 10. Subtract the 10 from both sides and then factor. Now, you might notice I've got x plus 10 there, which if this were just a quadratic equation that we were solving, we'd have a second answer here of x equals negative 10. Well, I didn't bother to write that down on my answer key because x equal negative 10 is outside the domain of the original equation, because we cannot take the logarithm of a negative number that's undefined. So negative 10 is not a valid answer to this problem. Only the positive 1 is a solution to the original problem. Okay, in problem number 11, we're supposed to figure out the number of years, or the amount of time measured in years, in order for a starting balance of $3,800 to grow to $9,500 at 4% compounded semi-annually, round to the nearest tenth of a year. So a 10 has 1 0, so remember what I said earlier. The number of zeros tells you how many decimal places. So tenths would be 1 decimal place in our answer. So semi-annually means twice a year. So that means that n in our formula is 2. The P stands for the present value amount, which is 3,800. The A stands for the future value amount, which is 9,500. R stands for the interest rate, and that is our 4% in this particular problem, but we need to change that to a decimal. So in order to change 4% into a decimal, we move the decimal point 2 places to the left and get 0.04. T stands for time, and that's what we're trying to find here. So first, I fill in my numbers into the formula, so I get this first line here. Divide both sides by 3,800. Now, that reduces down to just 5 over 2, or 2.5. So 2.5 is what we get when we take 9,500 divided by 3,800. So then take the natural log of both sides, because remember, we are trying to solve for a variable that is part of an exponent. Whenever you're trying to do that, best way to go, and in some cases the only way to go, is to take the log of both sides, or natural log of both sides. It doesn't matter, you can do either one. So the natural log of 2.5 is equal to, remember we get to bring the 2t down in front, 2t times the natural log of 1.02. So if I want to solve for t, which is what we're attempting to do, we need to divide by the 2 natural log 1.02, so that t is the only thing left behind on the right-hand side of this equation. So t is equal to the natural log of 2.5 divided by 2 natural log 1.02. Now be very careful when you type this in to your calculator. It is best, or at least it's shortest number of keystrokes, to get the right answer here, put parentheses around your entire denominator when you punch it in. So do natural log 2.5, close off the parentheses around the 2.5, divided by, start some parentheses before the 2 here, and then do 2 times natural log 1.02, close the parentheses for the 1.02, close the parentheses for the denominator, then press equals. That should give you the correct answer, which is approximately 23.1 years. Okay, here we have problem number 12. A sample of 250 grams of a radioactive substance decays at a rate of 3.2% per year according to the function. Okay, so we have A of t equals 250 times e to the negative 0.032 t, where t is time in years. How much of the substance will be left from the sample in 40 years? So all you have to do here is evaluate this function when t is equal to 40. So put 40 in place of the letter t, and the correct notation here is as I have it written down. You put the 40 both places where we have a letter t in our function, and then punch this into your calculator, and if you punch it in correctly, you should get 70 grams. Problem number 13. A certain radioactive isotope decays at a rate of 0.15% annually. Determine the half-life of this isotope to the nearest year. Okay, so 0.15% annually means we have a negative 0.0015 for that rate in our exponent. So decay means the rate's negative, and we have to change that percent into a decimal, so 0.0015. Now, half-life is the amount of time that it takes for half of a radioactive substance to decay. So 1/2 is 0.5, so we put 0.5 as equivalent of the A in the future and the A we started with, which is the A sub 0. A sub 0 stands for the initial amount. So if half of it is gone, then A of t divided by A sub 0 will always be 1/2 when we're looking for the half-life. So taking the natural log of both sides and then dividing by the negative 0.0015, we come up with t to be approximately 462 years. So it takes 462 years for half of this stuff to go away. That's what the half-life actually means, the amount of time that it takes for half of something to decay. Problem number 14. I did not care which method you used here. There were several ways to go. I chose to use what's usually called addition method, where somehow you add the two equations together so that one of the variables will cancel out. So if we multiply the second equation by -2, notice we'll have a negative 6y. And since the first equation has a positive 6y, when we add them together, the letter y cancels out. So that makes things a little bit easier to deal with. So you multiply by -2, add the two equations together, you should end up with x equals -4. If we replace the value of x with -4 in either one of these original equations, we'll be able to figure out the value of y. I chose to use the second equation, but either one would work and should give you the same answer. So the answer to this problem is the ordered pair, because this is actually a point where these two lines intersect. It's the ordered pair -4, 2. In this problem, I asked you to use Cramer's rule to solve. So we find our three determinants, D, the determinant of the coefficient matrix, D sub x, the determinant when we replace the x column coefficients with the constant terms from the opposite side of the equals, and D sub y. So hopefully this is self-explanatory. Just calculate those determinants, just a little multiplying and subtracting, and then x is equal to d sub x divided by d, and y is equal to d sub y, which is negative 78 here, divided by d. So negative 78 divided by 26 is negative 3. Now in problem 16, we have a non-linear system of equations. So Cramer's rule only works when you have, or at least it's only a good option when you have linear equations, or at the very least, your variable part in each equation is exactly the same. So in this problem, we don't want to use Cramer's rule. We don't want to use addition method. We want to use substitution. That is usually the best way to go with a problem like this. So taking the second equation and solving for x, we find out that x is equal to y plus 3. We substitute y plus 3 in place of the x in the first equation, and then simplify and solve. So we end up with y equals 5. Take that answer of y equal 5 and substitute it in place of the y back over here, and then we get x equals 8. So our solution is the ordered pair 8, 5. And here is the bonus problem. The important parts here, the units digit is 1 more than the tens digit. So if we say that the units digit is y and the tens digit is x, then we could say x plus 1 equals y. The sum of the squares of the digits would mean x squared plus y squared, and that would be 13. And solving this pretty much the same way we just solved problem 16 using substitution, x plus 1 goes in place of y, and if you work that out, x equals 2 is the only answer that makes sense, because it does not make sense for x to be a negative number. So we would not be able to use x equal negative 3 here. So if the tens digit, which is what x stands for, is 2 and the units digit in a number is 3, then the number is 23. So 2 tens and 3 ones. So that's 23. So good luck on the final, and I hope this is helpful to you.